This is Suvarchala working as an associate professor in the Institute of Aeronautical Engineering. A series of lectures in database management system. In this session, I'd like to discuss about normal forms. Last session, we discussed what are the flaws in database design, how these flaws can be overcome by using various techniques. So various anomalies were there actually. These anomalies are going to be overcome by using normalization technique. Normalization is a technique for producing set of relations with desirable properties given the data requirements of the enterprise being model. That means here normalization means because of the relation schema which we derived from ER model may face some problems. Insertion such as insertion anomalies, deletion anomalies, update anomalies, etc. These anomalies can be avoided or removed up to maximum extent through this process of normalization. For this normalization means dividing our or decomposing our relations into sub-relations to reduce the redundancy so that because of the reduction in redundancy leads to good database design actually. So this normalization technique produces a set of relations after decomposition. We already discussed in previous sessions, decomposition has to satisfy two major constraints or major properties. One is lossless join decomposition and another one is dependency preservation. These two were discussed in previous sessions. So in this session, I would like to explain how this normalization will be done and what are the rules and regulations to be followed. Basically, this normalization was initially introduced to developed by CARD, so considered as a father of relational database management in 1972. And this normalization often perform a series of tests on relation to determine whether it satisfies or violates the requirements of the any specified normal form actually. CARD initially defined three normal forms, that is first normal form, second normal form and third normal form. Boyce and CARD both together introduced a stronger definition of third normal form which is called as a Boyce-CARD normal form in 1974. All four of these normal forms, that is 1, 2, 3 and BCNF. These four normal forms are based upon functional dependencies. I already defined functional dependencies and how to make the dependencies as closure of dependencies, etc. These four normal forms are based upon the functional dependencies which exist on our relation schema. For example, if A, B are attributes or sets of attributes of relation R, B is functionally dependent on A, which is denoted by A determines B, if each value of A is associated with exactly one value of B. And also, I explained to you how this functional dependency is leading us to a key concept also actually. After these four normal forms, in 1977 and 79, further normal forms were defined, that is fourth normal form and fifth normal form were introduced, which are beyond BCNF. But they'll deal situations, very rare situations will occur in our real-time applications actually. These higher normal forms are subsequently introduced based upon various other types of dependencies. That means fourth normal form based upon multi-value dependencies and fifth normal form based upon joint dependencies. Other than functional dependencies, what I mean to say, which we will discuss in coming sessions actually. So, normalization considered as a producing a set of relation schemas which are having desirable properties. Not only fifth, more higher normal forms were also introduced theoretically. So this diagram represents how these normal forms are introduced actually. you observe the outer layer is 1NF, outermost layer is not in any normal form. The relation schemas are basically assume that those are not in any normal form. That is, those are not satisfying this normalization rules at all. Then based upon that, we will continue to make them to desired normal form. We will try to convert our relation schemas to any desired normal form. So 1NF, 2NF, you observe from normal forms, we can convert into first normal form. Our relation schemas will be satisfying the rules of first normal form. And from first normal form, you observe second normal form. Right? That means those which are relation schemas which are in 1NF, them only we will convert into 2NF. It's a step-by-step procedure now. We cannot directly convert into 2NF. First, we have to check whether it is 1NF or not. Then we have to convert into 2NF. If the relation schema is in 2NF, then we need to check for 3NF, third normal form. That means each normal form, it has to satisfy its own rule, plus its previous normal form must exist also, holds good. So that's why we represent it in the form of in circles. So any higher normal forms will be there. From there, fifth normal form, fourth normal form, BCNF, 3NF, etc. So we will start from this is our first stage of relation schema. Then we will convert into one normal form. After that only we will convert into second normal form, then third normal form, fourth normal form, and so on and so forth. What it indicates, each normal form should satisfy means already those relation schemas must satisfy the previous normal forms. Based upon these steps, various steps are normalization. So first 1NF, we will define each normal form in detail. So 1NF rule will be all multi-valued attributes have been removed from the table. That we'll discuss. That is as far as possible. All attributes must be of single valued attributes. And the second normal form means partial dependencies must be removed. Third normal form means transitive dependencies must be removed. And fourth normal form means any anomalies after 3NF, further anomalies are there, those must be removed by us. And we are going to have then fifth normal form and sixth normal form based upon our multi-value and joint dependencies. We will define each one of them and we'll see some examples of each of these normalization techniques actually. Now, in this example, that means from the relation schema, from one step to other step, we have to refine them. So, normalization is refinement of our relation schema so that whichever the anomalies we discussed in previous sessions, those anomalies can be reduced up to maximum extents. Most of the time, these anomalies are resulted because of redundancy. That means we have to reduce our redundancy up to maximum extent. We have to reduce. Please note that we may not remove redundancy from the relation schemas. We are going to reduce up to maximum extent. So this diagram represents whatever I explained till now. So table with multi-valued attributes will be removed. Remove multi-value attributes. Then we will enter into the first normal form. Then the relation schemas which are in first normal form, if any partial dependencies exist, those must be removed. Then we will enter into second normal form. And any transitive dependencies are there, remove them. Then we will enter into third normal form. Removing remaining anomalies, that is multiple candidate keys, if you remove, then we will enter into PCNF. Multi-value dependencies, remove, then we will enter into fourth normal form. By removing other anomalies through joint dependencies, we will enter into fifth normal form. Maybe higher normal forms were introduced theoretically, but up to fifth normal form generally we will consider. But among all these fifth normal, five normal forms also, practical applications, we will see that in the industry environment also, we will see that all relation schemas will be minimum in 3NF. Our relation schema must be satisfying minimum up to third normal form, minimum. At the most, it may be BCNF. We won't go up beyond that. Fourth normal form, fifth normal form, we won't check it all actually. Why we won't check that also we'll discuss in the next session as a closing part of the normalization. Why we are restricting ourselves normalization up to a particular extent only. Theoretically, they may be more useful to us in fourth, fifth, etc. further normal forms. But practical applications, most of the time, we may not consider, specifically in industry applications, the relation schemas will be up to third normal form, at the most maybe into BCNF, not further actually. So that's why we need to understand how this normalization process is going to be done. That is how to remove these multi-value dependencies, multi-value attributes, how to remove partial dependencies, how to remove transitive dependencies. What is meant by removal? Removal means nothing but we are going to decompose our relation into sub-relations so that the respective removal process is going to be satisfied. We'll see one by one. So what is the first step? A table which are having multi-valued attributes, we have to consider all tables are all relation schemas which are having multi-value attributes. Those multi-value attributes must be removed. Okay, so that is the first normal form. So a relation schema is in 1NF if and only if all the attributes of the relation are atomic in nature. What is meant by atomic? Atomic means single valued, or we may define it as a indivisible or undivisible. Undivisible means single valued. It cannot be divided into further. Such attributes are known as, it cannot have multi values, single valued attribute. Those are known as atomic. That only we defined in previously, multi-value attributes must be removed. That means each and every attribute must be atomic in nature in a relation schema, or then we can say that particular relation schema is in 1NF. So what is atomic? The smallest level to which the data may be broken down and remain meaningful still. You observe this relation schema was given your student table. So what the student table consists of? Student ID, student name, course ID, course name, grade. Right? So now a relation database design, practically it is possible to have a table like this. Student ID is there, course ID is there, course name is there, grade is there in our case actually. So for example, if you have student course details in a single table, we will have three attributes. One is student details, another one is course details, another one is results. You observe, student detail is a multi-valued. Student details consists of student ID, student name and date of birth. You observe course detail also multi-valued. It consists of composite attribute or multi-valued here. It consists of course ID, course name and area also, credits, number of credits. Results also, date and what is their percentage and grade. So based upon these things, we observe that certain data is not atomic here. It's not simple. It is a composite actually. So we have to convert means we have to divide our composite attributes into simple attributes. That is one way. That is student number is one attribute, student name and date of birth. Next course ID, course name, prerequisite. And what is the prerequisite? Prerequisite course is there, duration, date of exam, marks and grade. We made it as a individual attributes. If this is the table we able to generate, then it will be in the first NF because each attribute is undivisible further. It's each of these attribute is a single attribute and it consists of single valued also. So that's why then our table is in 1NF. Student course results table is 1NF. Previous table is not in 1NF because each attribute is of the type composite, which can be divided further. No, so we made it as a atomic, so it is in 1NF. We'll consider some other example. You please take department name and department number and department manager, social security number, department locations. Locations means here each department is located at various locations. Let us assume that. Now you consider the data in the table, department table of of the department table. So what are the attributes? Department name, department number, manager, social security number, locations. You observe. Okay, department name is a single valued and also simple attribute. Department number is also single valued and simple attribute. And department manager is also single valued simple. But coming to the department locations, multi-valued attribute. Previous example, we have seen composite attribute. Now this in this example, because composite attribute can be further divisible. But in this attribute, it's a simple attribute only, single attribute. Delocations is a single only. But multiple values attribute, multi-valued attributes. I explained these two kinds of attributes in the session ER model. So this department location consists of multi-value. You observe the research department exists at 3 locations. Administration exists at 1 location. Headquarters exist in 1 location. Maybe further, maybe more actually. So if any multi-value attribute is there, we have to normalize. To make it as a 1NF means it must be a single valued attribute. If it is a single valued attribute, how the data looks like? Because delocation should contain only one value. So that's why how many values are there in the first tuple? We have 3 values in the delocation. For 3 values, 3 tuples are generated. Research, department number as well as manager, social security number is same. But for 3, Belay and 1 tuple and another one is Sugarland, another one Houston is for another one. Anyway, for the other 2 tuples, only single or 1 value is there, we will get 1. What did you observe? Now my relation schema is in 1NF because all attributes are simple as well as single valued attributes, atomic. But you observe some redundancy is there. You observe research respect to department number and respect to manager was repeated number of times depending upon the number of locations where that particular department exists actually. Same relation but which is in 1NF but it is having some various more kinds of redundancy is there. You observe another example, first normal to convert. We have social security number, employee name, projects. This is another example for composite attribute, project number, hours. It is a composite attribute. We are dividing into project number and hours as separately so that employee project can be having single valued attributes. Or you can have a decomposition of the relation also. How can you decompose? I may be decomposing this relation into and social security number and employee name as one table and social security number, project number, hours as another table. Because of this decomposition, repetition can be reduced. So anyway, whichever the way you would like to consider, generally this is the rule we will follow. If it is a composite attribute, we will make into dividing our attribute into sub-attributes as a single valued attribute. We will keep the relation as it is. If it is a multi-valued attribute, we will, to avoid our redundancy, we will decompose our relation into 2 relations. All attributes without having multi-value attribute will be one table, and a multi-value attribute along with the primary key of the attribute is another table, like we have done in the C here actually. So first normal form disallows composite attributes, multi-value attributes, nested relations, attributes whose values for an individual tuple are non-atomic. All these are not allowed. So we have to see that each attribute will be in the atomic form. That is single valued, simple and individual actually. Okay. Now, but in general, what happens now? These kind of attributes we generally won't introduce in our relation schemas. By default, initially itself, most of the time, only for example purpose we have taken. But in real time, designing of a database, we don't use nowadays any multi-valued or composite attributes nowadays at all actually. So that's why generally 1NF will be default as a part of the definition of the relation itself we will consider. But to make sure that our relation schemas are in 1NF, we will check once again. So to move to the 2NF, first we will check whether that particular relation schema is in 1NF or not. Then only we will move to the 2NF. So that's why even the by default, we may take it granted that our relation schema design will be consists of only simple and single valued attribute to make sure that before moving to the further normal forms, we have to cross verify or check whether each attribute is of the simple and single valued attribute or atomic attribute. So that's why, as we discussed earlier, this department is going to be, instead of repetition is going to be allowed, we may consider the repetition, division, decomposition of relation can be considered. Okay, we'll move to the next normal form. Just check the data here. And each attribute is first attribute order ID, order date, customer ID, customer name, address, product ID, etc. Each attribute is individual attribute. Each attribute is a simple attribute. It's not composite. It is not further subdivided. So it is not composite attribute. And each attribute is having a single value also. So that's why such type of attributes are all atomic now. That's why our current table is in 1NF. Fine. But even though it is 1NF, it is not a well-structured table. Why? Because most of the data was repeated. You observe customer address and customer name and customer ID. Two are there. All of them are repeated thrice. Wherever customer ID is 2, then respective customer name and address were repeated. Similarly, wherever product ID is there, product description is repeated. If it is repeated, automatically repeated. So that's why we have to check such type of already we discussed, because of this redundancy, certain anomalies are going to be generated. To avoid this, we have to make our relation schemas will satisfy further normalization. That is, next normal form we have to check. So this is the table where it is in 1NF, but still it is not a structured table. It is not well structured table, so that most of the anomalies are allowed here in this example further. So that's why we need to make the current relation free of these anomalies. For that, what are these anomalies? We discussed in the previous table. A new product is ordered for a particular 1007 order of existing customer. Then what we have to replace or repeat the customer data. Again, we have to re-enter, causing duplication. Just now I have shown you customer number 2. For example, only one customer is, for example, you consider the fourth tuple, customer 6. Okay, customer 6 and the products are 11 and 4. I would like to delete any of these product. Then automatically related to the item information will be removed. If I am going to change the price of a product, a particular product, wherever it occurs, that product price must be changed. For example, product 4 exists twice. If I am increasing the decreasing the price, updating means wherever it occurs, it has to be get multiple updations. So, unable to insert certain data, deletion may result loss of information, and updation may need multiple updations. These are all anomalous exist. The functional dependencies in this table are like this. So the first functional dependency, order ID. Order ID determines these three. Order ID determines order date, customer ID, customer name, customer address. This is one FD. Another FD. Order ID determines order quantity. And product ID also. That is the combination of order ID, product ID. This is combination. This is key. You please observe underlined. This is a composite key. So this key determines order quantity. You observe the upper one. Another one is there. Product ID. So product ID determines the other product details. That is product description, product finish, unit price. Another dependency is there. Customer ID determines these two. These are the FDs with our table, the previous table. Already I explained you, FDs are the rules or constraints imposed upon our relation schemas. These rules or constraints are designed by either DBA based upon the requirements of the client. Sometimes. Okay, based upon the requirements of the client, that is business rules also sometimes. Now you observe here. Already we defined what is transitive dependency, partial dependencies in the previous session. What is the key attribute of this relation schema? Key attribute of the relation schema is product ID, order ID combination. That is composite key. Order ID, product ID. This is the combination of key. And these two determines only one attribute, order quantity. Order quantity is an attribute determined by the entire key attribute. Order ID as well as product ID combination. So this is a full dependency or fully functionally dependency. I explained to you what is fully. Fully functionally dependency means the attributes which are determined from the complete key is called as a fully functionally dependent. In this example, order ID, product ID determines and this is going to be considered as a order quantity is a full functional dependency because order quantity depends upon the complete key. That's why. You observe the remaining things. Another one is there. Here, order ID determines these three. What is order ID? It is not complete key. It is only part of the key. Order ID is part of the key. So, if it is a part of the key, what happens? The dependency is known as partial dependency. What is partial dependency? The attributes which are determined from the part of the key, not complete key. Those dependencies are known as partial dependencies. In this example, two partial dependencies are there. One is order ID determines this thing and another one is product ID determines. Because order ID, product ID both are part of the keys, not complete keys. Another one is there. Customer ID determines customer name and customer address. Transitive dependency, because both sides these consist of non-key attributes only. Left side is also non-key attribute, customer ID. Right side also customer name and customer address. It is a transitive dependency. We defined already transitive dependency as A determines B, determines C means A determines C will be a transitive dependency. Now this transitive dependency generally among the non-key attributes. Because of this, those anomalies are there. Now we will move to the second normal form. So the second normal form, generally how it is going to be defined and how will you make whether the current relation schema is in 2NF or not, we have to check. Then we have to consider how this schema will be converted into 2NF. So what is our step? Now the relation schema is 1NF. We have to move to the 2NF. So to convert into 2NF, the relation schema which is in already in 1NF, to convert into 2NF, we have to consider removal of the partial dependencies. In the previous example, we have seen two partial dependencies are there. Those two partial dependencies have to be removed. How to remove it actually? Now, the second normal form is defined as a relation is in 2NF if it is in 1NF and every non-key attribute is fully functionally dependent on the entire primary key. Every non-key attribute. In the previous example, only one non-key attribute was dependent on the entire primary key, but other attributes are depends upon the part of the key. So that's why those are partial functional dependencies. So that is every non-key attribute must be defined by the entire key, not by only part of the key. That is partial dependencies. Now you observe one more concept here. Part of the key. When the part of the key is going to be erased, if your primary key is a composite key, then only we will get problem of partial dependencies. Please all of you observe that. If your key is an individual key, if your key is a only single attribute, primary key consists of a single attribute, then no question of partial dependencies. Because part of the key doesn't erase, no? So remember all of you always, if the key attribute consists of more than one attribute, that is composite key is there, then only partial dependency concept may arise actually. So blindly you can check first. If your table consists of a primary key which is having a single attribute, there is no partial dependencies concept. Now, by considering the previous example, and it is not in 2NF as I explained you because two partial dependencies are there. Order ID determines order date, customer ID, customer name, customer address. Product ID determines product description, product finish, unit price. These two are, what are these two? These two are partial dependencies. Why? Because this order ID and product ID are the part of the keys. What is my key as explained you? Order ID, product ID. This combination, it is a composite. So therefore it is not in second normal form because partial dependencies exist. How to remove these actually? So to convert a relation containing partial dependencies into 2NF relation, we have to follow the steps. The first one, create a new relation for each primary key attribute. Combination of attributes are there, no? So for each primary key attribute, one relation schema is going to be generated. Similarly, for full functional dependency also, another schema will be generated. That is, a determinant in a partial dependency will make one subrelation. Similarly, a determinant with full functional dependency will make another subrelation. To move the non-key attributes that are dependent on these primary key attributes from the old relation into the new relation. As we already earlier explained, while decomposing this relation, it has to satisfy lossless join decomposition as well as dependency preservation also. Now you observe. What are the dependencies in previous example have? We have two partial dependencies. So for each partial dependency, one new subrelation was generated. Similarly, one full functional dependency, a new. So totally how many are there? Two partial dependencies, one full functional dependency. So totally three subrelations. This order relation invoice table is going to be decomposed into three subrelations such that each partial dependency related attributes will be in one relation and each full functional dependency attribute will be in another relation. As a part of that, first one, order ID, product ID determines order quantity, which is in our fully functionally dependency. Based upon full functional dependency, one table is there. What is the key now in this particular subrelation? Key is order ID and product ID combination, and non-key attribute is order quantity. Order quantity is fully functionally dependent on the key attribute. So that's why this satisfies in 2NF. It satisfies our 2NF. Now whenever we are having the second one, two partial dependencies are there, no? For each partial dependency, one subrelation will be generated. So what is the first subrelation partial dependency? Product ID determines product description, product finish and unit price. So that's why we generated a new subrelation with the first partial dependency. Right? And with other partial dependency, order ID determines order date, customer ID, customer name, customer address. With that, we generated third relation. What is dependency preservation means here? How many dependencies are there? One full functional dependency, second one, third one, fourth one. 4 FDs are there in this relation. After decomposing the relations into subrelations, all these dependencies must satisfy on at least one of the subrelations. Now you observe, the first FD was satisfied or holds good on this first subrelation. Second FD is order. Second FD is satisfied in the order subrelation. Third FD is satisfied or holds on this subrelation. Fourth FD is completely holds on this third relation. Now you observe, whatever the dependencies are there in the original relation, those dependencies are holds good in these on these subrelations. At least one of the subrelations, that particular dependency must hold. There should not be a dependency left over after this decomposition. That is called dependency preservation. All dependencies must hold in our one or more subrelations. At least one. So as a part of that, 1 is on first subrelation, 2 and 4 are on the second subrelation, third dependency is on second subrelation. That means all FDs are holds in our. Now you observe, these three subrelations are in 2NF because there is no any partial dependency. Here is a fully functionally dependency. Here also fully functionally dependency. Here also fully functionally dependency. We need not worry much also because what is our key? Except the first case. In the first case, the key is a composite key. Order ID, product ID combination. There only fully functional dependency. Here anyway single attribute is there, key attribute. It automatically, part of the key means no, nothing will be there, no. So that's why it's evidently all are in 2NF. So like that we have to convert our relation schemas which are in our 1NF must be into 2NF by removing partial dependencies. Removal of partial dependency means decompose our relations into sub-relations such that it satisfies two properties: lossless join decomposition. Another property is dependency preservation. Lossless join decomposition means each subrelation should have a candidate key or a primary key or a part of the key, so that we may get the original relation afterwards by joining them. Similarly, dependency preservation means all set of FDs are on original relation should satisfy at least one of the subrelations. Each FD of the set must be satisfied at least one of the subrelations. Another example, student ID, student name, course ID, course name, grade. You observe the possibility of partial dependency exists only when key is a composite key. Here, what is a key? Student ID, course ID, combination is a key. So, this key determines only grade. Student ID determines student name, course ID determines course name. These two are partial dependencies. This is partial dependency, this is partial dependency, and this is a fully functional dependency. Because it depends upon the combination, complete key. So FDs are represented. Student ID determines student name. Course ID determines course name. So what is this? Partial dependency, because partially depends upon partial key. Student name depends upon the student ID only. That is part of the key. Course name depends upon the course ID only, part of the key. So these are partial dependencies. This is fully functional. Any partial FDs are exist means yes. Two partial FDs are exist. That is, the first one is student ID determines student name, because student ID is a part of the key. Similarly, course ID determines course name. Course ID is also part of the key. Whenever a part of the key determines non-key attributes, it is a partial dependency. So, it is not in 2NF because it is having two partial dependencies. It is in 1NF. Each attribute is atomic. It is already in 1NF, but it is not in 2NF because two FDs are partial dependencies. So, therefore, it is not in second normal form. So, we are normalizing them. How to normalize? As I explained you, break the relation into sub-relations. Here, two partial dependencies are there. So, that's why for each partial dependency, one new table or a new relation is going to be generated. For functional dependencies, one table. So that's why I got student ID, course ID determines grade is one table. This is for functional dependency, fully functional dependency based upon that. And this is for partial dependency 1. This is for partial dependency 2. Now you observe 3 FDs of our original relation are holds good on any one of these sub-relations, each of them. So, fully functional dependency holds good here, and third relation, partial dependencies are holds good in one. Two partial dependencies and two relations. So, we are breaking our relation schema into more relations which satisfies both lossless join decomposition as well as your dependency preservation also. So that means lossless join decomposition means key attribute. Now you observe here it is student ID, course ID is a primary key. Part of the key is a primary key in the another tables. That is a foreign key you can consider in the next table. So here we are going to consider some other examples also there. Student ID, activity, fee, instructor. Activity determines fee. Student ID, activity determines instructor. If student ID activity is a combination of the key, then one is fully functional dependent, another one is part of the key. Activity determines fee is a partial. So that's why we can decompose our relation into sub-relations. So because of this second normal form definition, we will get the relation schemas which will satisfy these following properties. So consequences of the 2NF are the primary key consists of only one attribute. Most of the time, primary key consists of only one attribute. There cannot be partial dependencies in such relations, as I explained already. So remember, any relation schema consists of only one attribute as a primary key. There may not possibility of partial dependency existence. No non-key attribute exists in the relation. That is, all of the attributes in the relation are part of the. Every non-key attribute is functionally dependent on full set of the primary key attributes. That these are the characteristics or a condition satisfied the relation schema which are in 2NF. Then we will move to the third normal form. What is third normal form? Third normal form means the relation must be already in 2NF. You observe, already I have shown to you. These are the steps, means one by one only. Gradually we have to. Once the relation schemas are in 2NF, then we need to check whether those are in 3NF or we have to make them into 3NF. How to convert a relation schema into 3NF? We have to remove transitive dependencies if any exists. If any exist, we have to remove the transitive dependencies so that the relation schemas will be in 3NF. So what is definition? A relation is in 3NF if it is in 2NF and no transitive dependencies exist. Transitive dependency in a relation is a functional dependency between two or more non-key attribute. Remember, if any FD exists such that both left hand side and right hand side are non-key attributes, then there is a possibility of transitive dependency. So generally, a primary key determines all attributes, no? So that's why a primary key determines a non-key attribute. In turn, that again non-key attribute determines another key, means primary key determines again non-key attribute which is already existing one. So that's why transitive dependency. What is transitive dependency? If X determines Y and Y determines Z exists, then we will get X determines Z. If X is a primary key, even we are getting X determines Z, which is considered as a superfluous. Why? Because X determines Z already available. Because key attribute determines non-key attribute is quite evident. Now, if you observe this third normal form, previous example when we consider order normal form, we have converted into 2NF, but before that, a transitive dependency is there. What is transitive dependency? Order ID determines customer ID and customer ID determines customer name, customer ID determines customer address. What does it mean that by using transitive dependencies, we will get order ID determines customer name, again order ID determines customer address. Is it required for us? No. Why? Because it is already there. Because order ID determines these attributes is already there. It's only excess. We are giving already existing information again. We are showing it actually, which has to be removed so that it will be more efficient way. Right? So we have to convert a non-3NF relation into 3NF. First, what we need to check? First, our relations must be in 2NF first. Then we have to convert. To convert into non-3NF relation into a 3NF relation, for each non-key attribute, set of attributes will be there. A determinant in the relation schema create a new relation. That is, for each transitive dependency, create a new relation. One of them will become your key, so that transitive dependency can be eliminated. We are going to decompose our relation in such a way that transitive dependency related attributes will be one relation and other attributes will be some other relation. So the decomposition has to be done. In the previous example, we have three subrelations because first relation, basic relation is in 1NF. We decomposed into three subrelations to make it into 2NF. Right? So, order relation, customer relation and customer order relation. Already order relation is, for example, we have customer ID and order ID, order date. So when we have this, the relation schemas are converted in the previous example. So this is our example. All are into NF. To convert into 3NF, we have to check each subrelation, not a one. The main first relation is having invoice relation. It is in 1NF. We convert it into 2NF by decomposing the relation into 3 subrelations. Already explained. Now these 3 subrelations we have to convert into 3NF. We have to check whether it satisfies the property of transitive dependencies exist or not. If doesn't exist, it will be 3NF only. If it exists, then we have to convert. Clear? So that's why here, order relation, there is no transitive dependency. There is no any transitive dependency on this relation. Because only one dependency exists now. What is that? Order ID, product ID determines order quantity. Only one. And no transitive dependency. So that's why it is already in 3NF. Please observe that. I'll consider second subrelation. It is 2NF now. We converted, we got it to consider it into 2NF. Now here also I have only one FD. What is that FD? Product ID determines all these 3. Product ID determines this. Only one FD. There is no transitive dependency for me. What is transitive dependency? A dependency among the non-key attributes. But here only one FD is there. That is also fully functional dependent on the primary key of that particular relation, subrelation. So that's why it is already in 3NF. Here also no transitive dependencies. Please observe that each subrelation to make into 3NF, it must be in 2NF. Already those are 2NF. And check any transitive dependency exists or not. If doesn't exist, then they are already in 3NF. Like that, these two subrelations are already in 3NF. You consider the third one. While considering this third one, order ID determines customer ID, customer name, customer address and order date. That is a fully functional dependency. So it is already in 2NF. But one more dependency is there here. What is the dependency? Customer ID determines customer name, customer address. All these 3 are non-key attributes. All these 3 are non-key attributes. So there is an FD among the non-key attributes that may lead to your transitive dependency. In this example, order ID determines customer ID. Customer ID determines again this, which is a transitive dependency. So this is not in 2, it is not in 3NF now. Why? Because here a transitive dependency exists. So what I supposed to do? We supposed to do convert our relation schema into 3NF. So the first two subrelations are in 2NF. Again, all are in 3NF also because no transitive dependencies exist. But consider the third subrelation. Third subrelation, there is a transitive dependency. So we have to remove them. To remove them, we have to convert them into third relation, 3NF, by removing the transitive dependency. How to remove it? As we explained, the procedure is the transitive dependencies related attributes are in one relation schema and other attributes will be in the other relation schema. As a part of that, we will get here one transitive dependency exists between customer ID determines customer name, customer address. So that FD must satisfy my subrelation. No? So I am using a customer relation. I am using customer ID, customer name, customer address. This transitive dependency related one subrelation is there. Here, this is a key attribute. These two are non-key attributes. Only one FD exists. That is, customer ID determines customer name and customer address. And no transitive dependencies. So, no transitive dependencies means it is in 3NF. So, no transitive dependencies. So, it is in 3NF. Fine. Now, what about the other attributes we need to consider? What are the other attributes are left over? Order ID, order date, only two are left over. Order ID, order date. Can I make only those two attributes as another relation? For example, if I am writing order ID, order date as another relation. Fine, I can decompose. But remember, how can I join these two? If I am going to decompose like this, what happens? It doesn't satisfy the lossless join decomposition because there is no common attribute in these two sub-relations so that I cannot join afterwards to get my original relation. Loss of information may exist or a spurious tuples may result. That's why whenever we are making into sub-relations, we have to check if there is any referential constraints are going to be satisfied or not. So that's why order ID, order date and primary key of this table is also added here. So customer ID. What happens this customer ID? This customer ID is a foreign key here. Primary key will be order ID. So we decompose the relation into two sub-relations such that transitive dependencies will be, each transitive dependency will be in one sub-relation and other attributes, that is non-key attributes determined by the key attributes only, will be in some other relation by adding primary key of the sub-relation as a foreign key in the base relation. As a part of that, for transitive dependency, I got this one which is in 3 and F5, but the remaining attributes are only order ID and order date. I cannot make as a relation with these two attributes because such decomposition doesn't have a common attribute to rejoin them for further purpose. So that's why we should have a common attribute, that is customer ID. Now you observe customer ID is a foreign key here, which will be primary key here, which will be a foreign key in our order relation. Because of that, joining will become lossless join. It satisfies both conditions. Now this is a lossless join decomposition and dependency is also preserved. Order ID determines order date and customer ID determines preserved. Customer ID determines this preserved. Now all these are in 3NF. That means the original invoice relation is decomposed into totally 4 sub-relations. 1 and 2 I have shown in the previous slide, and here this is 3 and this is 4. 4 sub-relations are generated. All of them are in 3NF. All of them are in 3NF actually. Another example, 3NF. Course, section number, classroom capacity. Classroom determines capacity. Here composite key is there, you observe. Classroom determines capacity. Here classroom and capacity both are non-key attributes. We have already course, section number determines all other attributes because of the primary key. Now this become a transitive dependency. So that's what we have to eliminate. How to eliminate? Decompose. Break the relation into sub-relations. As I told you, the transitive dependencies related attributes will be another table and other attributes will be another table by having a common attribute as a candidate key. So that's why course, section number, classroom capacity will be one attribute. Classroom will be a common attribute. Here classroom is a primary key which is a foreign key here. What is primary key here? The combination of this course and section number is a primary key. So any transitive dependency exists. Transitive dependency related attributes are in another attribute, another relation, sub-relation. The respective primary key will be added into the base relation. So another example, shipment number, origin, destination and distance. What are the anomalies are going to be suffered with this and how these anomalies are avoided by making it to 3NF. The shipment is converted into 3NF so that what happens, whatever the anomalies are there, those anomalies are going to be reduced up to maximum extent actually. So these anomalies generally resulted because of this redundancy. So that's why the redundancy of the data must be reduced as far as possible. Because of this decomposition, the redundancy will be reduced. Why? Because I'm not saying eliminated. Some of the attributes are common, no? Those common attributes are going to be in some relations, some common attributes will be having common values, no? So that's why those are repeated. That's why we cannot say it is a completely eliminated. So the lossless joint property ensures that any instance of the original relation can be identified from the corresponding instances of the smaller relation. So we need not worry, because if we are satisfying this lossless joint decomposition property, if you would like to get the original relation, we can get because of this using joining property. Because and based upon this dependency preservation property, it ensures that the constraints which are imposed on our original relations are still holds on the subrelations also, maintained by the subrelations. So these two are not going to be violated. But even then, further some anomalies may be there. Those anomalies can be removed by using the definition of BCNF, Boy's God Normal Form, that we'll discuss in the next session. Okay. So in the next session, we will see that how this 3NF may suffer some problems and how to convert them into BCNF, and also we will see that what are the basics of fourth and fifth normal forms also. Thank you for watching this video.
Like, share and subscribe. Hit the bell icon for more updates.